Hello, good day. So we are group 4 and we are presenting on a question from classical control systems. So basically we have a circuit which we have to analyze using a transfer function. So we have the V in C1, that's the first capacitor, R2, a resistor R2, capacitor C2, and then out initially. So the circuit consists of an input voltage followed by a capacitor C1 in series, which is in parallel with I2 and C2 all combined, forming giving out a out. So structuring the circuit is a cascaded RC network with a series capacitor at the input and a series combination of a resistor and a capacitor forming the load, which is in parallel with the C1 as I already told. So since to we are asked for the transfer function of the circuit, we analyze the circuit in the Laplace domain using impedances. This allows us to convert the circuit into algebraic voltage divider problem. So basically, the other group members will come and explain and solve the question properly. Thank you.
I'm Alexandra Baini and I'm taking off from where Prince left off. So, to begin solving the problem, we must first understand the circuit structure. So, the input voltage, that's V1, is applied to the left terminals, and the capacitor labeled C1 connects the input node to the output node, meaning it is in series with the element. At the output node, a branch connecting resistor R2 and capacitor C2 is connected to ground. Since these two components lie on the same branch to ground, they are connected in series. This observation is critical because it tells us the circuit behaves like a voltage divider. Thank you. Mensa Francisca is my name, so I'm taking off from where Alexandra left off. So after interpreting the circuit, we now select the appropriate analysis method, which is 1. Laplace transform. 2. Voltage divider. And 3. Algebraic substitution. So, because the problem requires a Laplace transform, we would analyze the circuit in the Laplace domain. In the domain, the circuits are represented using the impedances, allowing us to use the algebraic expression to solve the circuit. Once the circuit is being converted, the circuit reduces to a series connection, feeding the load impedance, and then we use a voltage divider to solve for the circuit.
My name is Louisa, and then I'll be converting the elements to Laplace impedances. So, from Ohm's law, then you take Laplace. For capacitor 1, time domain relation. Then you take Laplace. So here is and then
So my name is Clarissa Chris, and I'll be taking us through the derivation of our load impedance. So our load impedance is derived using the voltage divider rule, which states that our V2 is of S is equal to our V1 of S times the impedance of the load 2. So substituting our transform values, we have our H of S being equal to our R2 plus 1 over SC2. This is all over 1 over S1 plus R2 plus 1 over S3. To further simplify, we multiply 2 by SC1, both the numerator and the denominator. So we have our final equation to be equal to SC1 C2 times R2 plus C1 all over SC1 C2 R2 plus C1 plus C2.
I'm Azuri Felix. I'll be talking about low frequency when S approaches zero. So when S is equal to zero into the transfer function, the outcome will be H equal to capacitor 1 over capacitor 1 plus capacitor 2. This means that the low frequencies, the output voltage is a fraction of the output of the input voltage. It is determined by the capacity ratio. This makes sense that when S approaches zero is the transfer function. Thank you.
I'm Desiree, and then I will continue with the high frequency behavior of the circuits. So to analyze the high frequency behavior of the circuit, we'll be talking about the transfer function of the circuit when S is approaching infinity. That's because in the Laplace domain, S represents the frequency, and then when it's increasing, that's approaching infinity. That's the high frequency behavior. So at this point, we will consider the transfer function and then analyze it with S being approaching infinity. So when S approaches infinity, that means that the factors of the transfer function, we have a transfer function as so this is our transfer function. And then And so when S is approaching infinity, that means these values of the capacitor becomes negligible as these values become dominant. So we'll have our transfer function as, that's when S is 1 as this. And since it's the same, we'll have the transfer function as being equal to 1. And this is a unity gain. So that means that when S is approaching infinity, we have the circuit having a unity gain of 1. And because of that, the inputs will be seen as the outputs, making it act as a high pass type.
I'm Samuel and I'll be taking us through the time, poles, and then the zeros. So because our answer to be h of s is equal to SC1, C2, R2 plus C1 out of SC1, C2, R2 plus C1 plus C2. The zero is found in the numerator and then the pole is found in the denominator. And then because S has a power of 1, it is what of the first order. And then we have our time constant, sorry. The time constant of the circuit depends on T is equal to C1 plus C2 out of C1 plus C1 C2 R2. So the time constant determines how fast the system responds to changes. So yeah. This shows that the resistor and capacitors together control the dynamic response speed.
Okay, my name is Brifu Insiankama Kofi. So this is our work, and this is our final solution. So this is our transfer function. So I'm here to talk about some applications of our circuit. So this type of RC network appears in signal conditioning circuit, audio filters, sensor interface circuit, and communication systems, and also control systems. Okay, so understanding its transfer functions helps engineers to predict function response, design filters, and control signal attenuations, improve system stability. Okay, so in summary, we converted the circuit to the Laplace domain, replaced components with impedance, and applied a voltage division, and simplified it to get our final transfer function, which is SC1 C2R plus C1 all over SC1 C2R2 plus C1 plus C2. Thank you.